Well, thank you for the opportunity to speak at the HPC User Forum this year. My name is Frank Alexander. I'm at Brookhaven National Lab, and what I'm going to talk about today is give you an overview of one of the projects that is part of the exascale computing project or program called ExaLearn. So ExaLearn, first of all, the overall ECP project is dealing with a number of application sub-projects. These are projects that span national security and energy security, economic security, scientific discovery, earth systems, healthcare, and so on, as well as a variety of software technology and hardware integration projects. And so it's a pretty diverse portfolio of applications in terms of different types of applications, different types of codes, and so on. And what another part of the project has been this development of these co-design centers, which are supposed to cross-cut across provide tools and methods across a lot of different applications. And so the one I'm going to talk about today is a project I've been leading called ExaLearn. It's a co-design center for exascale machine learning technologies. It's an 8-lab partnership. Argonne, Los Alamos, Berkeley Lab, Livermore, Oak Ridge, Pacific Northwest, Sandia, and Brookhaven. And it's been going on for about 3 years now, and we've made progress in a number of areas, and I'm going to describe that here today. Okay. So first of all, the overarching goals for ExaLearn are to provide exascale machine learning software for use by the other ECP application projects, in particular the ones that I mentioned in the previous slide. Other ECP co-design centers, there are, I believe, 7 of them now, dealing with particle methods and adaptive mesh refinement, for example, and graph models and so on. And so we're working together on those. We're also interacting with a variety of the DOE experimental facilities. These include light sources and nuclear physics experiments, nano centers, and so on, as well as leadership class computing facilities. So it's machine learning and AI, both benefiting high performance computing and benefiting from high performance computing. And so the goal is to establish multidisciplinary collaborations and learning technologies that cross-cut the ECP projects. And we work with not only with the other co-design centers and the other application projects, but also software projects and hardware integration as well. So when we started the project, we came up with a number of guiding principles for ExaLearn. As you all know, in this high-performance computing area, that there's a tremendous investment in machine learning and AI. In fact, that's only gotten the investment's only gotten larger since this project started back in the middle of 2018. It's probably investment is on the order of $100 billion a year, and maybe more in just R&D and machine learning and AI. And so this is really a small slice, a tiny slice of that. And so we really wanted to have an impact. And so we focused on tool sets that are applicable to multiple problems within the DOE mission that really weren't being met by the industrial community. Obviously had to have a direct line of sight to exascale computing and using exascale platform directly. We didn't want to replicate, it made no sense to replicate the capabilities that exist in other that exist in other commercial software and widely available packages, but we did want to leverage those because there's a lot of good work out there that can be leveraged. One of the things that's become that was appreciated when we started the project, but again has become more appreciated since we've been doing this, is the notion that one really should build in as much possible domain knowledge into the learning algorithms as possible. And some industry is doing this, but the performance of a learning algorithm tends to go up when you can build it, when you know more about your subject matter and you can build that into the algorithm itself. With a lot of DOE applications, we also care a lot about the uncertainty in our predictions. So not only will the algorithms make predictions, but we want to quantify how likely they are and our confidence in them. We'd also like to have methods, and this has become also more important as AI and machine learning gets more accepted broadly, is that it's interpretable and definitely reproducible. And finally, given that we're focused on scientific applications, we want to make sure that the methods we're using are based on mathematically well-grounded, have mathematically strong foundations. So in the project, we're actually developing a number of machine learning methods. The most prominent and are the most popular these days are deep learning methods such as convolutional recurrent neural networks and so on. But we're also looking at ensemble and random forest methods. We have a large effort in reinforcement learning for control, kernel methods, tensor methods, which have gained a lot of interest recently, especially since you can build in a lot of domain knowledge and make them more interpretable. Graph-based learning is part of our project, and then transformer-based methods, which have become more popular over the last few years, we're also using those. So in giving you an overview of the ExaLearn project itself, we've broken it into four main pillars. Surrogates, I'll drill down into each of these separately. So pillars, the development of surrogates, development of control algorithms, development for machine learning methods for design, and for solving inverse problems. And so for the surrogate models, in the area of surrogate work, the idea is to create, using machine learning and a variety of different methods, variational autoencoders and so on, and I'll explain in a couple of slides. So some of the work we're doing, I'll get into some detail for that. The idea there is to generate faster but also high fidelity models. In other words, replace very complex, expensive forward simulations of climate, cosmology, materials, etc., with much faster but high fidelity methods that are learned by machine learning tools such as generative adversarial networks and so on. And basically the idea is to replace, use machine learning to replace very complicated physics. And I'll give you an example that we've been applying it to in the area of cosmology. For control, we have a number of projects, but the idea is to use machine learning to actually control experiments as they are being carried out. And this is becoming much more popular, not just within the DOE, but elsewhere as well. And so that builds a lot. We're building a lot on methods in reinforcement learning and applying that into agent-based control of light source experiments. In particular, we're looking at temperature-based control for block copolymer experiments of phase separation of a particular type of polymers that form these very intricate structures and can be used for actually for designing, controlling design of microchips and so on at the nanoscale. We also have a project in design. And the idea here is to create physical, using methods of machine learning to create physical structures and that are optimized for particular behavior. And you can have in mind here molecular design, molecules being designed to carry out a particular task or to have certain properties and so on. And so we've been developing a lot of graph and convolutional neural networks to do that. And the idea there is, again, to respect the design new structures which respect the chemistry that you're after, for example. And then finally, we are using machine learning and AI methods to solve inverse problems. And so here, the goal is to back out the complex input structure from observed data. DOE has a number of facilities where this is the main, workhorse, that the main problem that they're solving. Light sources where you're getting scattering data, X-ray scattering data, variety of different scattering data. A spallation neutron source at Oak Ridge where you're getting a variety of neutron scattering data, and trying to infer the structure that generated that data. And so that traditionally has been solved by a variety of inverse methods, which are costly, and we're using AI and machine learning and deep learning to speed those methods up. So as I mentioned, in the area of surrogate models, one of the areas we're looking at is cosmology. And the idea there is that you have these extremely expensive forward cosmological simulations of the universe, that is starting from some initial condition, evolve the universe forward by treating, thinking of it as simulations of galaxies where you have n-body problems where they're solving gravitational interactions between these bodies, and the number of entities is on the order of trillions. And you integrate those forward in time using Newton's equations, basically, for gravitational interaction, and looking and seeing what parameters would lead to what structure in the universe that we are observing today, and then from that trying to infer what those parameters actually were. And so one of the things that's looked at one of the things that you can see in modern astronomical surveys is the power spectrum, so namely the distribution of matter in the universe. It has a certain statistical distribution, and you'd like to be able to, based on what you're observing, you'd like to be able to infer what the parameters of the universe are that would lead to that, that distribution. And so the way this can be, one way this could be done is by very expensive forward simulations. You pick a parameter, you run the forward simulations with another one of the exascale codes, ExaSky, for example, exascale projects, ExaSky. Run that forward for a variety of different parameters and see which, in some sense, agree with what you're viewing, what you're observing today. And then you say that, you could put some likelihood on those being the parameters which generated it. The problem with that is, the challenge with that is, those forward simulations are very expensive. And so, as I mentioned, in the surrogate model case, the goal is to actually develop models which mimic the forward simulation of the universe with n-body simulation, but do it much more cheaply, thousands of times faster. Nevertheless, which capture the physics you're looking for, and you can use that to help narrow down the search for parameters. And so that's really what I'm explaining in this slide right here. But once our initial foray is actually into cosmology, but one can easily, with those methods, apply them to other systems as well, which are very expensive forward simulations. So let me give you a little bit of an example here. The idea is one of the methods we're using are so-called generative adversarial networks. These are methods, and I won't go through the details here, but these are methods that are sometimes best thought of in terms of you have a teacher and you have an artist, someone generating fake art, and an expert detecting fake art. And so the idea is, by allowing both the generator of the art, the fakes, giving that person, or that person generates these images. A discriminator says those are fake or those are real. As time goes on, the generator becomes more successful at generating fakes, and the discriminator becomes more successful at determining whether something is fake or not. And as time goes on, they both become better at doing what they do. But the key here is that we are becoming better and better at generating synthetic data that looks like the cosmologies that we see, the cosmology we view today, in such a way that one could not discriminate that or distinguish that from something that is generated by a forward simulation that costs a lot to do. And so the idea there is, now we can rapidly generate, using generative adversarial networks and other methods, universes that look like the universe today and look like they came from these forward simulations. This is a very powerful tool. Now, the GANs have some challenges. GANs have some challenges. They tend to be very brittle. Sometimes they're very difficult to train. And so what we've done there is we've come up with methods at scale to be able to build in more physics that we would like. And so in the previous examples that I showed, the GANs were generating, quote, pictures of the universe we might see today without being told, and they have the right power spectrum, the right density distribution, without being told to do that explicitly. But we can also build that constraint in and say, we want the right density distribution, we want other constraints to be satisfied. And as it turns out, we can add a number of terms of a particular type to these generative adversarial models so that we capture more aspects of the physics that we want. And so that's worked out very well, and we've been able to scale that. So if you have physically motivated constraints, such as a power spectrum or multi-particle spectrum, higher order correlation functions, and so on, you could build those in, and then the system would converge to giving you the right physics toward that. And so again, these are very powerful, methods to generate data much more cheaply than forward simulations. Of course, they come with a caveat: you're not generating the forward simulation, so there's a lot that isn't going to be preserved. But it turns out that a number of the features that you're trying to preserve actually get preserved in the process. And these are being actively studied mathematically as well to understand how they work so well and where they break down. One of the things we're very excited about, discovered in the process here, is that it turns out that there are multiple levels of cosmological simulations that one would like to carry out. Some are so-called just n-body, so this is really just particles interacting with each other through Newtonian gravity, if you will, but on a cosmological scale. And you can also add more physics to that to be more faithful to what's actually happening in the universe, so-called hydrodynamic behavior as well. And so you can imagine the simpler problem of solving these n-body problems, and the more complex problem of having these n-body problems also coupled with hydrodynamic flow and so on, that is much more faithful to what's going on in the universe. The interesting thing there, well, the challenge there is that the much more physically faithful simulations are much more expensive computationally. But what we've discovered, and we're really drilling down on now, it's kind of exciting, is that it turns out we seem to be able to learn a mapping from the less expensive simulations to the higher fidelity higher and more expensive simulations. And we're trying to exploit that to find out, first of all, what the limits of this are, because this may be a very powerful way of doing simulations at one level of complexity and learning something about the physics at another level. You're not going to get something for free, so we want to understand how this all ties together and where this breaks down and how we can when we can trust simulations at one level of fidelity to make predictions at another level of fidelity. So another thing we're looking at, so shifting gears a little bit here, another area we're looking at in ExaLearn is the notion of objective-driven experimental design. And this appears all over in DOE applications, but in particular, you can think, I mean, there are numerous types of experiments. You can think of computational experiments, but also physical experiments. The idea here is we'd like to be able to learn to come up with an experiment or a computational campaign, a policy for carrying out computation that is optimal in a given way toward a given objective. So rather than just carrying out a large sweep of simulations of something and taking all the data from that, can we use ideas from machine learning, reinforcement learning, active learning, and so on to determine as we are getting information from simulations, which simulations one should then do next? And so it's really using machine learning to enable autonomous systems for computation, carrying out like very expensive computational campaigns, but that are goal driven. So you have a particular goal in mind. It will, you will learn a policy that will optimally or near optimally take you to that goal in limiting the amount of computational effort or whatever the limited resources are, typically computation. So where we want to go with this, of course, is at the end of this overall project is I mentioned those 4 areas, control, development of surrogates, inverse solvers, and design, is to actually tie all of those together in one particular application. And where we think we're going to go with that, we still have a few more years left in the project, our goal is to try that for at least one project, and we think we may end up doing that for a tokamak plasma fusion. So we would generate surrogate models for the plasma behavior, the tokamak behavior. From the surrogate models that we generated, we would then use those for training a real-time controller based on reinforcement learning. We would then apply the pipeline we've developed to solve some of the inverse solvers that we've developed in using machine learning to determine plasma equilibria configurations by solving inverse problems for the given physics. And then finally, with all of that information, tie this all together to actually design a control policy using our design pillar to design and optimize an overall tokamak design and control policy. And that general philosophy can be applied to a variety of different projects, but tokamak being one of them. But you can imagine applying that on the right there to wind plant, wind farm design, combustion engine design, and so on. And so that's where our ultimate goal is to tie these all together by the end of the project. So one of the reasons we're meeting, the reason we're meeting remotely this year, obviously, has been the pandemic. And what the Department of Energy has set up as a result of this is a so-called National Virtual Biotechnology Laboratory, NVBL. The goal of that has been to aid U.S. policymakers responding to COVID-19 with epidemiological information for decision making and so on. And really, the DOE's involvement is to leverage the supercomputing and AI capabilities of the DOE for designing and targeting therapeutics, and then also leveraging the considerable experimental facilities that the DOE has, in particular light sources for determining structures and neutron source for determining protein structure and so on. As part of that, 9 of the 17 DOE laboratories got together, Argonne, Brookhaven, Berkeley, Livermore, Los Alamos, Oak Ridge, Pacific Northwest Sandia, and SLAC got together for a project within the NVBL on high-performance computing and AI for molecular design. And so there was a significant investment in that, both formally through the National Virtual Technology Lab, but also 4 of the exascale projects were offered the opportunity, and we took them up on that to at least pivot temporarily to some work for COVID. And so that slide I showed you before of surrogates, control design, and inverse, we pivoted from our surrogate work in cosmology to the development of fast and accurate surrogates to replace large-scale, very complex epidemiological simulations. for the control project that we'd been applying to controlling experimental experimental control of systems undergoing complex systems undergoing phase transitions, we pivoted to designing optimal non-pharmaceutical interventions based on the surrogates that were learned from the large-scale epidemiological simulations. Where we did spend most of the effort from across the project really was in the area of design, where we were using graph neural networks and deep reinforcement learning for generating molecules specifically targeted for COVID-19 therapeutics. And then finally, our work on inverse problems, which was focused mostly on on more traditional materials, ended up getting focused on protein structure determination from the spallation neutron source data. And so we pivoted our project for about 6 months in the middle of 2020. And I'll describe a little bit about what we did in the area of molecular design. So when you're looking at what you're trying to do for molecular design is come up with drugs and therapeutics that both stop viral entry and/or stop viral replication. And so we have a framework that was developed also in the context of another one of our projects, multi-lab projects, called ATOM, Accelerated Therapeutic Opportunities in Medicine, or for Opportunities in Medicine, where typically what gets done is one has an enormous number of compounds. For example, you can see in the top left here, something on the order of tens of millions to billions of compounds. And you want to be able to predict which molecule and design molecules that will be useful for a particular task. And so you can carry out simulations at different levels of fidelity, very, very inexpensive, so-called inexpensive ones, where you can go from billions to hundreds of thousands, then carry out more expensive docking simulations, which narrow that down even further. And then likewise for all the way down to carrying out very expensive high fidelity molecular dynamics simulations, possibly even with quantum effects, which are going to be very expensive but very accurate physically. Using that with a variety of models, understanding what's happening at different scales for the system as well as for the system that's, for example, human, but also at the molecular level in terms of efficacy and safety and pharmacokinetics and whether these can be developed or not. And building a loop that takes all of that computational workflow from before, marries it with whatever domain knowledge you may have, and then feeds that works through a variational autoencoder, for example, to propose new molecules, which may have to guide new molecules which would have the properties that you're looking for, namely in terms of their efficacy and safety and PK and developability and so on, and then eventually carry out experiments. And so there's this overall design loop that we've repeated in a number of different parts of the project, but this is the basic structure behind it. So, for example, you can take as you take a so-called SMILE string, which is really a 1D representation of the molecular structure. Uniquely represents the molecular structure, encode that into a latent space, then move in the latent space to optimize for some desired properties, the ones I showed you from the previous slide, project it back to the SMILE string, and now you have a new potential new molecule that you'd like to see if how that what that molecule would do, both biochemically and then also in interaction with the overall system. So, and again, across a number of projects within ExaLearn, we were able to build this pipeline and also get it to scale to well over 4,000 nodes. So there was very good scaling behavior for this, and we're very excited by this. It was submitted by part of the ExaLearn team out of Livermore for Gordon Bell's submission, and was one of the finalists there. One of the, not to say amusing things, but one of the interesting things that emerged from this was my colleagues at Livermore were contacted by I think it was Pacific Power Company, when in doing these very large-scale deep learning simulations and learning and training, there were huge power swings you could see at the bottom that triggered some interest from the power company. So these types of simulations can be quite expensive, but also can cause tremendous power surges as well. Let me skip that. So let me summarize then by saying that we started in some specific areas that I described, cosmology and material science and so on, and as a result of COVID, temporarily pivoted into a number of areas. And that pivot actually not only, I think, contributed to a variety of COVID research, but also helped us in what we were originally doing. And so it really dramatically improved our ability to design robust and diverse small molecules that are optimized for specific criteria. We were able to rapidly train and retrain neural network architectures using leadership class facilities, and now that that was accelerated by COVID, the COVID work actually, and we're expected to have a broad impact across the field of scientific machine learning. The COVID work we did actually, I think, positions us better to produce AI molecular design across application areas, so not just for health and medicine, but also in the area of electrolytes and so on, which were the original interest was in. As well as for the inverse pillar, I mean, the work done on determining the structure can be used in a variety of different areas as well. And then finally, the work that we carried out while shifting also over to COVID in the control pillar, the investments we made there really have also led us to improvements with our ExaRL reinforcement learning framework, again, which can be used in a variety of different areas. And so with that, I want to thank you all for your time and attention, and I guess see if there's an opportunity to take questions. Thank you very much.